Good morning, guys. We are going to learn today about the difference between electrochemical cells and electrolytic cells. And I am going to, first of all, remind you about your electrochemical cells. So in this first example here, we have the reaction occurring between zinc. Oh, why do I not have a pen? Okay, let's try again. Zinc and copper ions. And we know the familiar setup is we have our two beakers, our zinc and our zinc ions, and we have our copper in our copper ions. And when we connect them externally with a wire and internally with a salt bridge, we're going to end up with a current flowing through the wire. Okay, and the current is going to flow because the zinc is a stronger reductant than the copper, and therefore we'll be able to, because we've separated these, we're going to be able to force the electrons to go through the wire. So at the anode, remember the anode is where you have your oxidation always. You have your zinc going to zinc ions and electrons. And those electrons are what gives this negative charge to the anode. So this build-up of electrons, so there's going to be a build-up of electrons, and that's going to cause the anode to have a negative charge. So at the other electrode, we have our copper. Let's have a green for copper. So we'll have copper ions accepting electrons and producing copper. Okay, and the fact that the electrons are being accepted here, we have a positive charge on our cathode. So there's our cathode reaction, and of course that is reduction. You'll remember red cat and ox. Okay, so reduction is at the cathode, the anode is oxidation. Right, so we know that the reason we can force the electrons to go through the wire here is that we've separated them to make sure that the zinc can't react directly with the copper ions. So that's our basic electrochemical cell setup. Let's have a look at this one. You've probably been spending a little bit of time with this reaction lately. So this is the reaction from the Bleach Battery. We have our aluminium at the anode. So our anode here. So our anode is aluminium going to aluminium ions. Then in this equation, what's happening then is that the aluminium ions are picking up some hydroxide ions from the bleach to make aluminium hydroxide. What we're seeing at the cathode is the reaction of the hypochlorite ion in the bleach. So what my question is for you, is we know that there are electrons going through the wire. We know that because we actually got a current. So electrons are definitely flowing. Okay, so we observed a current here. So we've observed a current. So my question for you is right here, the aluminium is in contact with the bleach. So yeah, Al in contact with the bleach, with the hypochlorite ion. So why is that not occurring right there? Why is that reaction not occurring directly? Why are the electrons going through the wire to react? The reaction's actually occurring here. Why not at the surface of the aluminium? Now I want you to pause the video and I want you to think about that for a second. You didn't pause it, did you? Pause it now and think about it. All right, so to explain this, we need to understand a concept called electrical potential. Now, electrical potential, it's kind of like you're very familiar with gravitational potential energy, but you're not so familiar with electrical potential. If you've done physics, you probably are quite familiar with it. But let's just go through this. We know that there is gravitational potential. We know that if here you are and you hold a ball, so if you're holding it, you hold a ball above the ground. So you've got that ball 1 meter above the ground. You know that it has a certain amount of gravitational potential. Okay, so you know that you have lifted it up, you've done work on the ball, and it now contains some stored energy. And there's a difference in gravitational potential between this point here and the ground. And therefore, when you let go of the ball is going to fall. So you know, you do understand about gravitational potential energy. Okay, so let's talk about electrical potential. Let's get rid of, whoa. Hopefully you already copied that down. So let's talk now about electrical potential. If we have a look at our standard reduction potentials, where the metal sits, so we've got our copper here, and we've got our aluminium here, and they are at different places on the reduction potential table. There is a difference in electrical potential. I don't know what I'm doing here. So there's difference in electrical potential. And just like the ball, when you've got a high gravitational potential energy here, and you've got 0 gravitational potential energy here, when you let go, that ball is going to move from higher potential to lower potential. Well, if you've got here, our copper has a lower electrical potential, and our aluminium has a higher potential, then what we're going to look at is the electrons wanting to go from higher potential to lower potential. So up here, no matter what, there's this copper being at a lower potential and this aluminium being at a higher potential, we want the electrons to flow. The electrons will want to flow from the aluminium to the copper. So the copper's kind of sucking the electrons toward it. And therefore, because of that difference in potential, the reaction is actually going to occur over here rather than at the surface of the aluminium. So this is what we observe also when we're looking at the corrosion process. We looked at when you have zinc and iron connected, that the electron flow is from the zinc to the iron, and that causes the iron to become the cathode. So it's similar to that. All right, so I'm going to shift to a different whiteboard now. We're going to talk about spontaneity. We're going to talk about whether a reaction occurs naturally. So spontaneity is whether a reaction occurs naturally and what we find is that positive values for our electrical cell potential or our reduction potential are spontaneous reactions. So we can see that everything here, everything there happens naturally. And everything here won't happen naturally. And so when we're talking about potential difference, which is what drives the electron flow, what we've also called this for an electrochemical series is E0 cell. So if you calculate your E0 cell, remember it's the oxidant minus the reductant. So if we do the E0 cell for the copper and zinc, so for zinc copper 2, then zinc is our reductant and Cu2 plus is our oxidant. So what we're going to see is that our zinc is, where's our zinc one? There it is. So our E0 cell is going to be the copper ion here, which is plus 0.34. And then we're going to subtract the zinc one, which is negative 0.76. So what is that? So we add 0.76, that's 0.7. Did I get that right? Yep. So 1.0. So what we're looking at here is that this is a positive value, and therefore that's going to be spontaneous. That means as soon as we connect them, the electrons are going to flow. So what that means is all of these reactions, they happen naturally in reverse. All of these are reversible reactions. That's what that arrow means. So none of them will happen in the forward direction as it's shown. They will only happen in reverse, which means that if we're going to want those reactions to happen, we're going to need to apply an electric current. So we're going to need to force the electrons to go in the opposite direction. We're going to be therefore working against the electrical potential. And remember to work your electrical potential against the gravitation, to work your gravitational potential against the gravitational field. You had to do work, you had to put energy in to lift the ball up. So we're going to need to put energy in to reverse the electrical potential as well. And we're going to talk more about that in our next video. Okay, how do I stop screen sharing now? Oh, there we go.